Hello my good friends, Derek Deschamps here for Internetworking Influencers, your source for free Cisco certification training for network engineers. Welcome to day 3 of our free CCNA 100-105 ICND1 training course. The Internetworking Influencers CCNA 100-105 ICND1 training course is comprised of 13 videos, each focusing directly on a set of specific items on Cisco's official exam topic list. Today's episode will cover item 1.3, describe the impact of infrastructure components in an enterprise network, including firewalls, access points, and wireless controllers. Item 1.4, compare and contrast collapse core and 3-tier architectures. Item 1.5, compare and contrast network topologies, including star, mesh, and hybrid. Item 1.6, select the appropriate cabling type based on implementation requirements. And lastly, item 1.7, apply troubleshooting methodologies to resolve problems, including perform fault isolation and document, resolve or escalate, as well as verify and monitor resolution subtopics. If you haven't yet looked at Cisco's official exam topic list, I've included a link to it in the show notes. As a reminder, today's video has a set of free practice questions that are available on our website at internetworkinginfluencers.com that will help you brush up on the topics you learned today. The questions are a true representation of the types of questions you'll face on the actual exam, so be sure to check those out once we're done. Building on the more fundamental network devices like hubs, switches, and routers that we learned about in episode 1, today we're going to start things off by covering some more advanced infrastructure components, namely firewalls, access points, and wireless controllers. A firewall is used to control the flow of traffic between networks. It performs advanced filtering to either block or allow traffic based on predefined security rules. So for example, if we want to allow our local area network to connect to the internet, we can install a firewall between the two networks and control exactly what types of traffic can flow in and out of our network. A firewall like the Cisco Adaptive Security Appliance, or ASA, allows us to add interfaces to security zones. We can then apply security policies to the different zones to control what traffic is allowed to flow between zones. For example, a typical network will consist of an inside zone for the local area network and an outside zone for the internet. We can then configure the firewall to allow traffic initiated from the inside zone to access the outside zone. However, deny traffic initiated from the outside zone from reaching the inside zone. This configuration will allow the local area network to access systems on the internet, however, deny anyone from the internet from accessing the local area network. A third zone, called the demilitarized zone, or DMZ, is often added to provide a place for servers that need to be accessed by systems on the internet. For example, a company's web server, external mail server, or external DNS servers are often placed in this zone. This allows us to configure policies to allow systems on the internet to access the DMZ servers without exposing our inside zone or local area network. A stateful firewall like the Cisco ASA monitors the connections that pass through it and retains the information in a state or connections table. This allows the firewall to apply security rules based on the state of the connection. An example of a stateful firewall's advanced filtering capabilities would be blocking a packet due to an incorrect sequence number or flag in the data stream. The next infrastructure component we will look at is the wireless access point, or AP. A wireless access point like the Cisco AeroNet series is responsible for forwarding data between the wired and wireless networks. It's worth noting that a wireless access point is different than a standard wireless router people use in their homes. A home wireless router is more of a hybrid device that combines firewall technology, an Ethernet switch, and a wireless access point in one device. An access point can operate in one of two modes. In autonomous mode, the access point is not only responsible for forwarding data between the wired and wireless networks, but also handles all management functions for the wireless network, including authenticating devices and defining the wireless LAN name, or SSID. This mode is generally used in networks with a small number of access points. In lightweight mode, the access point is only responsible for forwarding data between the wired and wireless networks. In this mode, all management functions for the wireless network are handled by a wireless LAN controller, or WLC. A wireless LAN controller is used to manage multiple lightweight access points, or LAPs, from a central location. The wireless LAN controller handles all management tasks for the wireless network, including wireless device authentication. All configurations for the wireless network are stored on the wireless LAN controller and downloaded by the lightweight access points. This greatly simplifies management, making it an ideal solution for large-scale deployments. All wireless traffic is tunneled through the wireless LAN controller, which allows wireless devices to roam seamlessly from access point to access point when changing physical locations throughout the wireless network. The next topic we will cover today is network architecture, by going over how Cisco recommends our local area networks, or LANs, be designed. A local area network, or LAN, is a network that is contained in a small geographical area, such as an office, building, or university campus. A LAN is designed to be easily expandable and to provide fast data transmission. A wide area network, or WAN, is a network that connects LANs together over large geographical distances, such as offices or buildings in different cities. WAN connections usually consist of communication links that are supplied by communication service providers. As I mentioned, the network architecture we will cover today will focus on LAN design. The three-tier model for network design contains an access layer, a distribution layer, and a core layer. The access layer is responsible for providing network access to the end users. Access layer switches are where the end user systems are connected. In a typical large network, access layer switches are placed in the wiring closets on each floor to provide connections to the end users. The distribution layer acts as an interface between the access layer and core layer. Access layer switches are connected back to one or more distribution layer switches, which provide them access to the rest of the network. In a typical large network, each building would contain two larger distribution layer switches, which would connect back to each access layer switch. The core layer is the backbone for the network and is used for connecting the distribution layer switches in multiple buildings together. The core layer is designed to be a high-speed, highly reliable, low-latency transit path between distribution layer devices. The three-tier model is generally used in large campus networks that contain multiple buildings. A more commonly used model is the two-tiered or collapsed core model. With a collapsed core model, the distribution layer and core layer are combined together in a single layer. This helps reduce the costs involved with having a third layer, and provides most the same benefits as the 3-tier model. With this model, the distribution layer switches also act as core switches, providing a central connection point for the access layer switches, while also acting as a transit path to access both internal and external networks. There are 4 different network topologies or patterns in which network devices can be connected, which you should be familiar with for the exam. A star topology occurs when you have one central device that connects to multiple other devices to form the pattern of a star. While a star topology is simple to implement, the central device provides a single point of failure and also acts as a bottleneck, as all traffic must pass through it. A full mesh topology occurs when all devices are connected to each other. While this topology is fully redundant, leaving no single point of failure, it is difficult to implement due to the large amount of connections required. A partial mesh topology occurs when some of the devices are connected to every other device on the network, while other devices are not. This design requires less connections than a full mesh, while still providing some redundancy. And lastly, a hybrid topology occurs when 2 or more topologies are combined together. When connecting network devices together, it is important to choose the right type of cabling. The first type of cable you should be familiar with for the exam is called unshielded twisted pair, or UTP cable. A standard Ethernet cable, such as a Cat6 or Cat7, is a type of UTP cable. A standard Ethernet UTP cable is comprised of 8 copper wires that are grouped together into 4 pairs and terminated on the pins of an RJ45 connector. For 10BASE-T and 100BASE-T standards, only the 4 wires connected to pins 1, 2, 3, and 6 are used for network communication. PC network cards, routers, and wireless access points transmit on pins 1 and 2 and receive on pins 3 and 6, while switches and hubs receive on pins 1 and 2 and transmit on pins 3 and 6. With 10BASE-T and 100BASE-T, a straight-through cable takes the wires connected to pins 1, 2, 3, and 6 on one end of the cable and connects them straight through to pins 1, 2, 3, and 6 on the other end of the cable. This makes a straight-through cable the correct cable to use when connecting 2 devices that transmit on different pins. For example, a straight-through cable would be used for connecting a device that transmits on pins 1 and 2, like a PC network card, router, or wireless access point, to a device that transmits on pins 3 and 6, like a switch or a hub. With 10BASE-T and 100BASE-T, a crossover cable takes the wires connected to pins 1 and 2 on one end of the cable and crosses them over to pins 3 and 6 on the other end of the cable. This makes a crossover cable the correct choice to use when connecting 2 devices that transmit on the same pins. For example, if you needed to connect 2 routers together, you would use a crossover cable. With 1000BASE-T or gigabit Ethernet, all 8 wires of a UTP cable are used. Devices can now transmit and receive on the same wire pair. A gigabit Ethernet straight-through cable connects the wires on pins 1 through 8 on one end of the cable to pins 1 through 8 on the other end of the cable. A gigabit Ethernet crossover cable takes the wires connected to pins 1 and 2 on one end of the cable and crosses them over to pins 3 and 6 on the other end of the cable, in the same way as 10 base T and 100 base T. It also takes the additional wires connected to pins 4 and 5 and crosses them over to pins 7 and 8. UTP is the cheapest form of network cabling and is also very easy to install. UTP is generally used for short distances, with most UTP standards reaching a maximum distance of 100 meters. The next type of cable you should be familiar with for the exam is fiber optic cabling, sometimes referred to as simply fiber, and other times referred to as just optical cabling. Optical cabling is comprised of two thin optical fibers, or strands of glass, that carry signals by transmitting light. When connecting two devices with optical cabling, one side of the connection will transmit on the first strand, and the other side of the connection will transmit on the second strand. Fiber optic cabling is usually more expensive than UTP cabling. It is not as susceptible to interference as UTP. However, it can suffer from attenuation if bent beyond its minimum bend radius. Fiber optic cable is a good choice for long distances, with some standards for multimode fiber reaching a maximum distance of 550 meters, and some single-mode fiber standards reaching 5 kilometers. The Institute of Electrical and Electronics Engineers, or IEEE's 802.3 Working Group, has developed many different standards for defining the various network speeds and the types of cabling to be used for Ethernet networks. These standards all begin with the numbers 802.3. Some of the more commonly used standards include 802.3, also referred to as 10 base T, which defines 10 megabit Ethernet. 802.3U, also referred to as 100 base T, which defines fast Ethernet. 802.3Z, which covers gigabit Ethernet over both multimode and single-mode fiber. 802.3AB, also referred to as 1000 base T, which defines gigabit Ethernet over UTP cable. And lastly, 802.3AN, or 10G base T, which defines 10 gigabit Ethernet over UTP. The last topic we're going to look at today is troubleshooting methodologies. The exam will test your knowledge of troubleshooting methodologies both directly by asking you questions about the troubleshooting process, and also indirectly through questions that require you to troubleshoot network problems. Cisco's official exam topic list has broken down the troubleshooting process into 3 steps. The first step in the troubleshooting process is to perform fault isolation and document the results. This is achieved by first defining what the problem is, and then gathering any further information you may require before attempting to isolate the issue. Once you've isolated the issue, it is recommended that you document the root cause. This is usually achieved by providing an update in your company's issue tracking software. The second step is to resolve the problem or escalate it. If the device that is causing the problem is one that you manage, and it is within your ability to fix the issue, the next step is to resolve the problem. When implementing your solution, it is recommended that you only manipulate one variable at a time until the problem is resolved. If you do not manage the device, or if it is beyond your ability to fix it, you may choose to escalate the issue to management or a higher level of support. The third step is to verify and monitor the resolution. Once you have implemented your solution, you will need to verify that the symptoms have been resolved. Depending on the type of problem, you may need to monitor the solution over a period of time to ensure that the symptoms no longer exist. In further episodes, we will go into more detail on how to troubleshoot specific issues as we learn about the different technologies. We will also learn about the built-in Cisco iOS tools that are available to help you troubleshoot and resolve problems. And that brings us to the end of Day 3 of Internetworking Influencers CCNA 100-105 ICND1 training course. Don't forget to complete the free practice questions for today's material, which can be found on our website at internetworkinginfluencers.com. The free questions will help highlight the key points that Cisco will expect you to know for the exam. Also, if you enjoy our free training and would like to show your support, please check out our Patreon page, where we offer numerous perks to our supporters ranging from additional practice questions and detailed study notes for each video, to direct access to our instructors to answer any questions you might have. I'll be back next time for Day 4, where I'll cover IPv4 addressing and subnetting. I'm Derek Deschamps for Internetworking Influencers. Thanks for watching.